So today we're going to talk about water and some of its very, very, very strange properties. Water is such a common substance to us that we don't think about how weird it is. But for its size, water is way weird. So let's look at some of these characteristics. First of all, as it says here, water has a high surface tension. Now, when we think about surface tension, it's that inward force or pull that tends to minimize the surface area of a liquid. What does that mean? It means it's trying to pull it into like a spherical shape. And like virtually all of the characteristics of water, it's due to hydrogen bonding. When all of these water molecules are hydrogen bonded to each other, they're pulling inward, and so they're attempting to decrease that or minimize that surface area, so they tend to go into a more spherical shape. If you've ever watched some of the movies where they're showing water in outer space, you'll see it floating around in these nice little spherical shapes. Water droplets, you can see water bugs running across the surface of a pond. All of these are examples of the surface tension of water. Now we can break down the surface tension of water by using a surfactant. A surfactant is simply a surface active agent, and it lowers or breaks down the surface tension of a liquid. Soaps and detergents are things that act as surfactants. So if you look microscopically at something that's dirty, like some clothing or whatever, and it may look smooth, but it has all of these ridges in it whenever you look at it microscopically. And when you're trying to clean, that dirt gets trapped in these ridges. And if you put just plain water on that piece of clothing or a dish or whatever, it kind of scoots along the surface. And so it'll clean across that surface, but the high surface tension of water, it won't get down in there and dissolve that material, that dirt. So when we put a surface active agent in there, it will, like detergent again, or soap, it will break down that surface tension, break down the hydrogen bonding, and it will get in there and clean out those crevices. So that's what the soap is for, the surface active agents. Water, another characteristic, water has a low vapor pressure. Vapor pressure is the tendency of molecules at the surface of a liquid to escape. And water has a very low vapor pressure, an incredibly low vapor pressure for its size. And yes, you probably guessed it, hydrogen bonding is the reason for this. As the water molecules are held by that hydrogen bonding, they just don't have a very high tendency to escape. Now, as you start heating up the water, you'll get those water molecules moving faster and faster, and eventually get to the point where they have enough energy to break those hydrogen bonds, and then they'll start escaping at a more rapid rate. But a low vapor pressure is another characteristic. A third characteristic is that it has a high heat capacity. We talked about heat capacity before when we dealt with the MCAT equation. Remember, the heat capacity is the amount of heat it takes to raise the temperature of 1 gram of water, in this case, by 1 degree Celsius. And for water, it takes an incredibly large amount of heat to cause the temperature of water to increase compared to other substances its size, similar substances, because of, again, that hydrogen bonding holding onto those molecules. They don't start moving and increasing their motion as fast as other molecules and other types of substances might, so their temperature simply does not raise as quickly. So once again, hydrogen bonding affected in that as well. Water has a high boiling point. Based on its size, water should be a gas at room temperature. But thanks to hydrogen bonding, it takes more energy to change water into a gas than other molecules its size. When you look at the heat of vaporization for water, the amount of heat it takes to change a gram of water into a gram of gas or steam, it takes a very large amount of energy, 2,257 joules per gram. And even to melt water requires a large amount of energy compared to other substances, 334 joules per gram. So hydrogen bonding, once again, makes it require lots of energy to break that down so you can start melting or boiling water. One of the worksheets that you're going to be doing deals with a heating curve, what we call a heating curve. And let's say this is the heating curve of water. There are 5 different states, or 5 different phases, maybe we can say, stages in the heating curve. The first one, going from A to B, this is the point at which, when you're heating something up, and let's do this in red. When you're heating something up, this is going to be at the solid stage, heating a solid at this point. And you'll notice that the temperature is increasing. Temperature is going up this way as the time is progressing. So as the temperature increases, we're heating the solid. We get to a point in time between B and C where there is no change in temperature. At that point, what is happening is that as that heat is being added to that system, it's being used not to increase the temperature, but to start breaking down, in this case, hydrogen bonding, if we're dealing with this being water. And this is the point where melting occurs. There is no temperature change, no delta T at this point. No change in temperature. So then once everything is melted, then it will start heating up the liquid. So the stage from C to D is heating the liquid. And once we reach the boiling point, notice that we go for an extended period of time with no change in temperature. This is a point where all of the heat that's being added to the system is being used to completely break down those attractive forces, in this case hydrogen bonding for water. And at this point, we're going to have the vaporization occur, boiling. And finally, let's go ahead and write this down because it's important. There's no change in temperature anytime we have that phase change. And finally, the last one, from E to F, that's when we're heating up the gas. So those are the 5 stages of any heating curve. Cooling, we can do the same thing. Let's go in the opposite direction. If we're going in this direction, we're talking about cooling the gas. When we reach this point, then, as it keeps giving off heat, we are in the process of condensation. And then as we continue to cool it, we're cooling the liquid at this point. And we have freezing. And finally, cooling the solid. So going in the opposite direction, it's cooling curve. So those are the different stages that heating/cooling curve goes through. Another characteristic of water that's very strange is that solid water or ice is less dense than liquid water. Solid ice, we don't think it strange at all to see ice cubes floating in a glass of water, but that is actually very, very, very strange. Most solids, by far most solids, or most substances, the solid is more dense than the liquid. But look what happens. I know by this time you can't be very surprised that hydrogen bonding is due to this. When we have the liquid over here, liquid water, the liquid water molecules are all just kind of jumbled together. They are attracted somewhat by hydrogen bonding. That's what makes water puddle together, is that hydrogen bonding, positives and negatives, and they're just kind of flowing around each other. But when the water starts to freeze and cool down, the water jumps into these rigid 6-sided structures, and those 6-sided 3-dimensional crystal structures have a lot of empty space in between. And that empty space in between those crystal structures causes the density of the solid water, the ice, to be less than when it's a liquid. So that's why we have lakes freeze on top instead of from the bottom up. Our ice cubes float. So again, a very, very strange property of water. Water is also known as the universal solvent. It dissolves many different substances, and that's because of its very polar nature. We talked about that in an earlier lesson, the fact that those two lone pairs here on one side of the oxygen, we end up with a partial negative charge on the oxygen side and a partial positive charge on the hydrogen side. And when you drop something into water, an ionic compound, for instance, that's made up of all of these ions, sodium chloride with its positive sodium and negative chloride ion, the water molecules attack. And when they attack, look how they line up. Now, this is just one layer, but they actually form layers of water around these ions, layers of water molecules. And you can see that in the case with the sodium, the water molecules are lining up so that their negative oxygen ends are close to the positive sodium, which makes sense, opposites attract. And when it comes to the chloride ions, the positive end of those water molecules, the hydrogen ears, if you will, are attracted and surround the chloride ion, which in essence splits apart those ions and dissolves them. It is called solvation. This is the solvation of the sodium chloride. Now, what happens if the attraction between those two ions, the sodium and chloride, let's say it's silver and chloride. Silver and chloride, or the compound silver chloride, is notorious for not dissolving in water. And that's simply because the attraction for the positive silver with the negative chlorine is so strong that the water molecules are not able to overcome that. That's why we get a precipitate. A silver chloride is formed in a chemical reaction. In general, like dissolves like. Polar substances tend to dissolve in polar solvents, while nonpolar substances tend to dissolve in nonpolar solvents. Like dissolves like. And we can see with that polar nature of water why those ionic compounds would dissolve. Now, another factor, another characteristic is that, or something that water does that's kind of neat. You've seen this earlier in the year when we looked at our hydrate and we determined the formula of a hydrate in the lab, that water molecules are often part of the crystal structure of many substances. They're like trapped in that crystal structure. They're called hydrates or hydrated compounds. And I do want you to be familiar with their names and what they mean. When you see something called cobalt-3 chloride dihydrate, for instance, what that means is that you've got the normal cobalt chloride lattice structure, but for every cobalt, and keep in mind, if cobalt's at 3+ and chloride's at -1, we're going to have CoCl3, and I could write that better. It's not very good. If cobalt's a 3+ and chloride's a -1, then we're going to get the CoCl3 formula. And the dihydrate simply means that attached onto that, for every 1 cobalt chloride unit, we're going to have 2 water molecules. Sodium sulfate decahydrate, sodium's a +2, sulfate's a -2, so we have, sodium is not a +2, sodium is a +1. And sulfate's a -2, so we're going to end up with a formula of Na2SO4. The fact that it's decahydrate, that's deca stands for 10, tells us there's going to be 10 water molecules attached on or in that crystal structure for every 1 sodium sulfate unit in that crystal lattice structure. Hydrates are pretty cool. the water that's trapped in that crystal structure is called water of hydration. And when a crystal, a hydrated crystal effloresces, that means that it loses its water of hydration. So efflorescence is losing the water of hydration. You see hygroscopic compounds quite a bit. You may not realize, and probably have never called them hygroscopic compounds, but they are substances that actually remove moisture from the air. You're going to see them being used as desiccants or drying agents in electronic equipment, shoes. I've seen them in beef jerky. And they always are in packages that say "do not eat." I can understand putting "do not eat" in your beef jerky for a package in your beef jerky, but I have yet to figure out why you would put have to label a package "do not eat" that came in your shoes. Evidently, it's happened. But a deliquescent compound, these are some of my favorites, and one of my very favorites is cotton candy. Deliquescent compounds are compounds that are so hygroscopic they will actually turn into a liquid as they remove water from the air. If you've ever had cotton candy on a very humid day, you'll notice those drops of liquid forming on the cotton candy, and that's because cotton candy is so hygroscopic. It's becoming deliquescent. It is removing water from the air and turning into a liquid. So, pretty cool. Kind of a weakness for cotton candy. Finally, the last one. Water conducts electricity very well when certain types of substances are dissolved in it to make solutions. These are called electrolytes. Electrolytes are substances that are very important in our bodies. Using them in our bodies to conduct electrical signals is incredibly important if we want our brain to be able to tell any part of our body to do anything, like our heart to beat or our legs or arms to move. Substances that will act as electrolytes if they're dissolved in water are soluble ionic compounds and strong acids and bases, and we'll talk about acids and bases later in this unit. Non-electrolytes are substances that do not conduct electricity when they're in an aqueous solution. Covalent compounds. Sugar is an example of a covalent compound that will dissolve in water, and if it does dissolve in water and you try to conduct electricity through that water sugar solution, it will not conduct. Insoluble ionic compounds, if they don't dissolve in the water, they're not going to produce the ions and they're not going to conduct electricity. And we'll talk more later about being able to look at different kinds of compounds and decide whether they're ionic, knowing that if they're ionic or they're a strong acid or base, that they're going to be an electrolyte, and otherwise they're not.